And here in day 2, topic is obviously still probability, but in day 1 we just really focused on the probability of an event, and today we're going to dive into a few other types of probability problems. For example, the union of two events. Okay, if you see a problem that refers to two separate events and the basis is really one or the other occurring, it would follow this formula. Okay, you could use or in place of that symbol for U. You might have seen that before if you've ever studied sets previously. The upside down U equates to the word and. All right. So basically, the word or in probability always goes with addition. Okay. We just have to be careful that we take out the possibility that the two events that were mentioned could happen simultaneously on a single trial. Now that might not be possible if you have two events that are what's called mutually exclusive. That means the probability of A and B is equal to 0. If that were the case, then it would follow that the union of those two events, A or B, it would follow the formula above. You just don't have the part at the end because you don't have to worry about if the two events could happen on the same trial, because if they're mutually exclusive, that's not possible. And here's an example. Okay. Heads or a face card. I'm going to say that drawing a heart is H or F, a face card. I could look at these separately and just say, okay, what's the probability of drawing a heart plus the probability of a face card, but I just need to check, and maybe it's possible these two events are mutually exclusive, but I do need to look, is it possible to draw a heart that is also a face card? Could both of those events happen on one draw? Well, in a 52 card deck, 13 are hearts, 12 are face cards. Okay, now it's possible that could be my solution if I'm convinced that there are no hearts in the deck that are face cards, but that's not the case. There are 3 of them. Okay, the king, queen, and jack of hearts. And what's going on is those 3 face cards are counted in those 12, and they're counted in those 13. So those 3 particular cards I've counted twice, which I obviously don't want to do. I just want to count them once, so I need to take them out. That would all come out to 22 over 52, which would be around 0.423. All right, here's one that has an example of some events that are mutually exclusive. Okay. Oh, it's got their years of service and the number of employees that have served for that long. Okay, this is a relatively simple one, but it gets to the idea of events that are mutually exclusive. All right, so what are the odds from this particular company that we select an individual that's been there 4 years or less? I don't think the problem told us. So you'd have to add up all of those employees. This is going back to the probability of a single event, kind of like what we did in day 1. There's 529. 157 have been there 4 years or less, that's about 0.297. Okay? Now we go over to part B, and now it says, what's the probability we pick an employee that's been there 9 years or less? Okay? All I have to do is just add up those two outcomes. Okay? It's not like the problem we just did with the cards, where I have to be concerned about taking out the possibility that both of these outcomes could happen on the same selection. Okay? I have two groups that I need to add together, 0 to 4 and 5 to 9. Nobody fits in both of them. Okay? And that's why these events would be mutually exclusive. We've got to take the 157 that have been there 0 to 4 years plus the 89 that have been there 5 to 9. And obviously the probability goes up. The odds are now about 0.465 that you get an employee that's been there 9 years or less. All right, so another big concept is that of independence. We already mentioned how that symbol is and, right? So now you're not talking about one event or the other happening. We're talking about both, okay? We're talking about both. You can just multiply the individual probabilities if, take a look at the definition below, if you're convinced that that's true, that the outcome of one has no bearing on the outcome of the next. So it says that random number generator will select 3 integers from 1 to 20. What's the probability all 3 numbers are less than or equal to 5? Okay. We do get to assume on this problem that each selection is independent. Whatever number was selected on draw number 1 doesn't affect 2, nor does it affect 3. So really all you have to look for is really the one event that's described. There's 20 numbers to choose from. We're looking at the possibility that the number selected is 5 or less. There's a 1 in 4 chance on each of these that we would get a number that's 5 or less. The whole idea with independence is that probability doesn't change. Now that's not so bad to write out, but if you wanted to be a little more efficient, you could just factor in the number of selections, which is 3, by doing 1/4 to the 3rd power. And the odds would actually be pretty low, 1 out of 64, that all 3 numbers would be 5 or less. Got some data here from 2016 about adults in the population that get news from the internet every single day. That's what that 62% is saying. If you got your news from the web, 4 or 5 days a week, but there was a day or two that you don't, you're not included in that 62%. Let's say we choose 10 people at random. What's the probability we get 10 individuals, all of whom get their news from the web every day? Here we definitely want to use an exponent because it's 0.62, right? But assuming each individual pick is independent and how one person gets their news isn't affecting the next, we would just do 0.62 to the 10th power. The odds are actually somewhat low, right? But remember, those odds are that we get 10 out of 10, right? Every single person says, yes, I get news from the web every day. All right, last kind of new probability topic here, because we've covered the union of two events, which is kind of like one or the other happening. We talked about mutually exclusive. We talked about independence. Here is a complement. Okay, a complement, and we'll see it in our last example here, basically comes up with, sometimes it's a better approach, instead of saying, hey, what's the probability of this event, what's the probability that it doesn't happen? Sometimes that's easier to calculate. Really what's going on here, it's honestly a pretty simple idea. Take your event A. P of A is the probability that that event happens. Typically when we talk about the complement, we put an apostrophe on A. That means that A didn't happen. Those two probabilities always have to add up to 1. Okay? Think about that just in totally abstract, general terms. You have an event. Okay? You are guaranteed with that event, whatever the context may be, that one of two things is going to happen. That event will either take place or it won't. Okay? Regardless, the context doesn't matter. The actual, numbers that we're dealing with don't matter. They always add up to 1. Okay? So you'll see, for some problems, it's easier to kind of switch it and say, hey, what are the odds that that doesn't happen? For example, a manufacturer has determined that one of the machines they use averages 1 faulty unit for every 1,000 it produces. What's the probability that an order of 200 units will have 1 or more faulty units? Okay, 1 or more. So there's two different approaches we could take here. We could try to, because it says 1 or more, we could try to get all the different possibilities. 1, 2, 3, 4. What are the odds that 5 are faulty? There's an absurd number of cases that we'd have to deal with. Okay, to the point that that would really be impossible to do. But if we go with the complement, we could say, really, when it says 1 or more, the opposite is 0. What are the odds that the order is perfect? That's the complement. Okay, it's not the probability that we're looking for, but a perfect order would be the exact opposite to what it's describing. All right. So let's talk about P of F. F is a faulty unit. And it said the odds that that happens is 1 out of 1,000, or 0.001. Okay? Now right off the bat here, I could do F complement, which would be a faulty unit. And the odds of that would be 0.999. Okay, we've already used a complement once. The work we just did right there involved a complement. All right? 1 out of 1,000 chance that that unit is faulty, 999 out of 1,000 that it's not. Okay? So I could take that probability and I could raise that to the 200th power. Okay? So this would be the odds that you put together an order of 200 units and all 200 are functioning properly. We would get that. Okay, 0.819. Now if we are making sure we're reading the problem closely, okay, we know that that's not our answer. That's not what the question asked. We don't want the number for, hey, what are the odds that the order is perfect? Again, what it's really saying is, what are the odds it's not? What if one or more, any number of them aren't working? Well, this number is going to help a ton because the question is asking for the opposite of that. About 0.181, or essentially just over 18%.